Hello, my name is Bobby Schultz. I'm an undergraduate at the University of Minnesota Twin Cities studying electrical engineering and computer science. Now, today I'd like to talk to you about a kind of transistor. Now, previously we've talked about transistors and I referenced some of the different varieties of them. This is one of those different varieties. Previously we've talked about BJT, or the binary junction transistor. Now, today I'd like to talk about a MOSFET kind of transistor. Now, you have FET transistors, which are field effect transistors, and then you have a subcategory of that, which is the MOSFET. MOS meaning metal oxide semiconductor, which actually has to do with how the transistor is built. Now we're going to be talking about a subcategory of that today called logic level MOSFETs. Now I know this is a lot of terminology, but don't worry, we'll sort that all out later. Now what a logic level MOSFET is it's a very robust transistor that switches, meaning switches on and off, at a quote logic level. This means either 5 volts or 3.3 volts. Now, why do we care? Well, this is built to work with a microcontroller, like an Arduino or something like that. Now, you can switch very high loads using just a signal from a microcontroller. And now we're not limited on our voltage that we're switching like we were before with a BJT transistor. Now we can take a 5 volt logic line and say switch a very large load of say 12 volts or something like that, or even higher. For instance, I have one here. This is a N-type. For instance, there's both an N-type and a P-type, of course, just as before with transistors. This is an N-type logic level MOSFET. Now this guy right here has absolute maximum ratings of 60 volts and 30 amps. Now it can constantly dissipate 80 watts of power. Now if you compare that to one of the BJT transistors we were working before, they can dissipate less than 1 watt of power continuously. So as you can see, these are incredibly powerful, certainly compared to what we've worked with before. Now these have 3 pins apiece. That is going to be your gate, your drain, and your source. Now we're going to talk about what those are and what you hook those up to in a minute. So let's go now and let's talk about the pin setup and the math of some of this and how it switches and where your load and where your power is going to be. So let's talk about that now. Alright, so now let's actually talk about the circuit involved in a logic level MOSFET. Now, here is the symbol for a MOSFET. This is an N-channel MOSFET, so it's going to be switching on the negative side. And this is just like the one that I showed you before. So now let's talk about what kind of goes around here. So we're going to be switching this on the negative side. First, let's talk quickly about these 3 pins. Here you're going to have your drain, your source, and your gate. Now your drain and source are either going to be sourcing current from something or draining it from another, and then your gate is going to be what's actually going to switch it on and off. So in this case, for an N-type, you're going to have up here, this is just going to be your load, whatever your load happens to be. And then up here, you're going to have your positive voltage, whatever you're running this load at. Say this is a motor, an LED system, what have you. So this is going to be your plus V sub S. And for this MOSFET, that can be up to 60 volts. Now, of course, you'll want to verify what yours is per your individual data sheets, but just to give you an example of what it could be, get rid of that. All right. So then you're going to have your plus V sub S there, your load, and then the current is going to flow out of your load into the drain of your N-channel MOSFET, and then your source is going to go out to ground. Now your gate. What is your gate going to be? Well, because this is a logic level MOSFET, your gate voltage is effectively independent of your voltage up here at your drain, which is going to be plus V sub S or some amount of it. All this really cares about is it greater than your switch on condition? And for a logic level MOSFET, your switch on condition is going to be between 3.3 volts and 5 volts usually. Some of them are very low, down to 2 volts only. Of course, you'll want to find this on your data sheet. It will be under gate threshold voltage or words to that effect. But in most cases, you'll be very safe with 3.3 or greater. So when this is at 3.3 volts to 5 volts in that range. So a high side of a microcontroller, for instance, you put a output on your Arduino, you're going to get 5 volts. So when that sees a logical on, it will then be switched. And then this, of course, is going to go to ground or be referenced to ground, that same common ground. Now, one other consideration, though, and this is purely due to the fact of how it's actually constructed, is the fact that your, as I was saying before, this is a MOSFET, so metal oxide layer. You have a metal oxide layer in here, and that has an internal capacitance. So what that means is that, let's say we do this. Let's say we switch it on. We apply 5 volts to this, and then, it's running, and then we release that 5 volts. Now, in a common transistor, like a BJT, that would be fine. Our transistor would go off. So say we let this line float then at, somewhere between 0 and 5 volts, but certainly less than 2.5, it will switch off. However, with a MOSFET, that is not the case. Because of this metal oxide layer, you get what's called an internal capacitance, which means even though we stop supplying a logical on signal here, there is an internal structure that's going to cause this gate to still read 5 volts or close to it for a long time if we don't do anything to change that. So you'll be able to switch it on, but then it will never switch off. This is a problem. Now, how do we fix that problem? Well, it's very simple. We just need to add what's called a pull-down resistor over here. And this is going to be a value of, say, 10K, 10 kilo ohms would be a very safe value for this. Now, what is this going to do? What this is going to do is we apply our 5 volts here, and that will switch this on. Then we remove that 5 volts. So then this goes to float then. We've removed the logical pin. This then will pull that down, and it will make sure that the 0 we want to see here is actually seen, because it will drain this internal, quote, capacitor that I've been talking about, and it will cause this gate to then see 0 volts rather than 5 volts lingering on there. So that will allow you to actually switch this properly. So this is very important for a MOSFET. And that's your main difference between a MOSFET and just a common BJT transistor. So now let's talk about P-type MOSFETs. Now here we have a P-type circuit. Now our pin assignments here are going to be a little changed. We're going to have our source up here, our drain down here, and this is once again going to be our gate. And if you think about it logically, you can understand why this is. Source means that it's sourcing current from that location. In the previous case of the NPN, we were sourcing current from ground, if you will, that we were switching whether or not the current will flow to ground or not. In this case, we're sourcing whether or not current will flow from our positive voltage source to ground. So it's just sort of changing the orientation of things. And then, of course, we're going to have our load down here. That's our load, a motor or some LEDs, what have you. And then up here, we're going to have our positive voltage source plus V sub S. And then down here, we're going to have our ground. So now on our gate, once again, we are going to be looking for actually, I apologize. In this case, we'll be looking for a low voltage to turn it on. When this goes to ground, it will be on, meaning that we naturally want it to be off. So we're going to actually tie it to a plus 3.3 to 5 volt, whatever you're working with, line. We're going to tie it to that with a pull-up resistor in this case. So around that same value, a 10K would work very nicely. So now what this is going to do is this is nominally going to pull it up to this value. And then we are going to switch it on whether or not we're pulling it down to ground. So say we want it to run, we close this switch, and then it will run, and then we release this switch, and then this pull-up will pull it back up to this value and cause it to turn off again. So again, this is very important. principle of a pull up or pull down resistor. Just in this case, we have a pull up resistor as opposed to a pull down resistor. Now, in general, these are very similar to the BJT transistors we talked about before. The key difference is in this pull up or pull down resistor, and it's important to understand that, of why that's important, because otherwise you can run into issues where you're switching it on and off, but of course it won't switch on and off because this pin is floating at some value. So this is an important aspect of it. So now let's actually go and make a circuit. We'll actually make one with an N-type. So let's actually go and build this circuit and then see how that works. Alright, so we talked a little bit about the design of the circuit using a logic level MOSFET. Now let's actually look at some of the setup of it. So this is a demo of the circuit that we discussed. This is using an N-channel MOSFET. So it's going to be switching on the negative side. So here we have just an LED just to indicate whether or not the MOSFET is on. And we're driving it with high side through a resistor. And then the low side is going out through the source to the drain, to ground. And then here we have our pull-up resistor right here, which is pulling up the gate of our MOSFET. And then this button right here is just going to drive that gate line high. So we just have a power supply going here, so let's turn that on. So you'll see right now the LED's off, and that's because the gate is being pulled down by our pull down resistor. And now let's drive that pin high. So when we drive the pin high, the LED comes on. Now, when we release it, it's going to go off. That's again because of this pull down resistor. Now, I'm talking a lot about this, but that's the only real difference in the setup of this between a traditional transistor. And so it's an important thing to understand. Now, let's just take a look at how this is going to operate without this pull down. So we remove the pull down resistor, and as you can see, it spontaneously comes on. Probably my hand being near there caused the capacitance on that metal oxide layer to jump up enough that it switches it on. And as you can see, no matter what we do with that, it won't turn back off. So it's an unstable setup. You know, it could stay off until you hit this button, but there's obviously no guarantee of that. Unless, of course, we pull that line down and make sure that it stays down, like so. And then it operates just as we designed. So this is a very simple operation, but a very powerful operation. Right here I simply have a LED being switched on and off, but as I discussed before, a MOSFET like this can handle far more. This can handle approximately 80 watts of power dissipation and has absolute maximum ratings of 60 volts or 30 amps. Depending, and then a max of those two at 80 watts. So a very powerful device for switching very large loads without any issue. And of course, this pin right here, this button, could easily be replaced by a digital pin on a microcontroller or something like that. So this is a very powerful circuit. So I hope that this setup has helped you, and I hope this video has helped you understand MOSFETs and logical MOSFETs a little bit more.